Hello everyone, welcome back to Calculus 2. So in this video, we're going to talk about 1.7 integrals resulting in inverse trigonometric functions. So we've been talking about many different type of function, and depending on the function, the technique of integral is slightly different. Do you remember if we are dealing with the composition function, you're going to use substitution. And if you have a log function or exponential function, there's a particular techniques we're going to utilize. So what we're going to do today, we're going to focus on inverse trigonometric function and the relationship with the integral. So I'm going to just show you three important techniques. So the title is integral resulting in inverse trigonometric function. So for example, you are dealing with the function and we are taking the integral. We never know what kind of function you're going to talk about, but there is a very unique function that brings us the inverse trigonometric function outcomes. For example, what is the inverse trigonometric function, such as a sine inverse function, or cosine inverse function, tangent inverse function. We have a couple inverse function that you learn in pre-calculus, but here we're going to introduce three important inverse trigonometric function: sine inverse, tangent inverse, and secant inverse. And then here is the thing. I'm going to write one sentence. If a function, we're talking about this function, we don't know what kind of function you're going to talk about, but there's a function, and if you are dealing with the function, okay, includes perfect square numbers in the denominator, then we consider the integral resulting in inverse trigonometric function. So here is the thing. This is the function that you're gonna deal with. So let's say I have 1 over radical a squared minus u squared. And then if you're taking the integral with this unique function, the outcomes will include sine inverse. Another one, there's no radical, but a squared is a perfect square number. So you guys know what the perfect square number, such as you're multiplying the same number twice. 1 times 1 is a 1 square. So 1 is perfect square number. 2 times 2, 4 is a perfect square number. 9 is a perfect square number. So you have a 16, 25, whatever you're multiplying same number twice, we call these numbers are perfect square numbers, correct? So if you have a perfect square numbers in the denominator form, right? These are perfect square numbers. Then we're going to consider the integral resulting. The outcome will be, what do you think? You're going to see the inverse trigonometric function. So this is a particular technique we're going to utilize in chapter 1.7, and I will show you the example. So sounds like a little bit abstract, but it's a pretty simple. So take a look at it. Your outcome after you take the integral include inverse trigonometric function. We are particularly looking at sine inverse, tangent inverse, secant inverse. If you have a perfect square number in the denominator, for example, I don't know, you are just thinking about some function that include the perfect square number, always the outcome will be include sine inverse. If you have a squared plus u squared, perfect square number, the outcome always include tangent inverse. And you have a u times u squared minus a squared, and then the outcome is going to be secant inverse. And there's a little bit of, information you're going to deal with later. So I'm going to highlight it and I will show you the example. So just remember, if a function includes perfect square numbers in the denominator, then please consider the integral resulting in inverse trigonometric function. And here we go. I'm going to show you the example. So I already have the three techniques here. So we have the same information, number 1 to 3. So let's take a look at this. So here I see 1 over radical 1 minus 9 x second power. So you feel like maybe this is a composition function, as you see that 1 minus 9x second power has been subbed into the radical. So yes, of course, you might be able to use a u substitution, and then you can find out the answer. But here in 1.7, we are going to use the following technique. Take a look at the denominator. 1 minus 9x second power, okay? So 1 is 1 times 1, as you see that. 1 times 1 is a perfect square number. 9x second power look like 3x times 3x. You're multiplying same number twice. It is also perfect square number. So what I'm going to do, I might be able to utilize one of the technique that I show you here. Okay. One thing we're going to simplify. Let's factor by 9. So what I'm saying is here, we have a radical 1 minus 9x second power, factor by 9, and then 1 minus 9x second power. If I factor out 9, the inside will be 1 over 9 minus x second power. Because if you do the distributive property, it's going back to 1 minus 9x second power. So this equation is the same as 1 over 9 minus x second power. They're the same thing. So I'm going to highlight it. 1 minus 9x second power is the same as 9 times 1 over 9 x to the second power. Are you following? So then, what do you guys think? We can simplify more and more. I'm going to bring the outcome we got. 9, 1 minus 9 x second. And then I can break them, separate radical 9, 1 over 9 x to the second. And radical 9, we know that it's going to be 3. And we have a 1 over 9 x to the second. Are you guys okay with that? So here I factored out. And then let's look at that one more time. 1 over 9 x second power, what is that? That's also perfect square number. 1 over 9 is the same as 1 over 3 times 1 over 3. X is x times x. So now you have to make the decision. One of the technique will be used to find out your outcomes. So when I look at, right, when I look at the, number, this is the number constant square minus variable square. So what I'm going to do, I can keep simplifying. By the way, we have all integral here. Everywhere we do have integral. I can bring 1 over 3 to the front. So we have 1 over 9 minus x second dx. We always have a dx at the end. Okay. So now what I'm saying is, look at this now. 1 over 9 minus x squared. This is exactly a square minus u square form that you can utilize the first technique. So the answer is a is what? So this is going to be a squared. 1 over 3 times 1 over 3 is 1 over 9. So a will be 1 over 3. U will be x. So therefore, 1 over 3 integral radical 1 over 9 x second dx, they said, according to the first technique, will be sine inverse u over a plus c. And then we know what the u, which is x, and then a is a 1 over 3. And then you can simplify, and then let me just minimize a little bit. This is going to be, I can bring this one to the top. sine inverse 3x plus 3, and I have a 1 over 3 actually in the front. So that's your answer. So it's like a little bit of work. So what I'm saying is, if you want, you can take the composition function so that you can utilize U substitution. You will get the very similar answer. But what I'm saying is we are thinking about another perspective to solve this problem. So the technique is, when you look at the denominator of this fraction, right, in the given function, check it out the denominator. And then if it involves with the perfect square number, your outcome will be one of the inverse trigonometric function, either sine inverse, tangent inverse, secant inverse. And then I just modify a little bit because the 3x second power is not really matching x second, right? Everything should be without the constant, so that I just factor out 9 so that we simplify right there. And then when I see this, 1 over 9 is 1 over 3 times 1 over 3. So a should be 1 over 3. And x squared is a u squared, therefore u should be x. So according to the technique, this is the first one. U we define as a x, a we define as a 1 over 3, so that you can plugging in, you will get that answer. So this is not really memorizing things. We just follow the technique so that you can find out the answer in a shortcut. Okay, so don't worry about it. We're gonna practice a little bit so that you will feel, oh, actually that's what they mean. Okay, so let me show you more example. So take a look at it. You can pause the video and you can write down on your notebook what we are doing. So basically we're, utilize the techniques, and then when especially the given function is getting involved the perfect square number in denominator, the outcome of the integral will be one of the trigonometric function, inverse trigonometric function. So let's take a look at example 2. So we have this one. I'm going to modify a little bit. So x times radical x second minus 16. Look at this. X second 16. We know that it's a perfect square number. And then what do you guys think? This is exactly matching with third one. U is a constant. U is the variable. A is a constant. So x is a u with the radical x squared u squared. This is exactly a squared constant. So what I'm saying is we define u is x. A should be 4. So the outcome, 1 over a secant inverse u over a plus c. Excuse me. And then we know every information. A is a 4. Secant inverse x over 4 plus c. That's it. That's the answer. You see that it's a very shortcut. The first one was a little bit, require you to do the work. The second one, simply, we know the pattern. This is matching with the third one. U times the radical x squared minus 16. That's exactly u times the radical u squared minus a. So u is the x or any variable. A is the constant. So you can think about it. All right, let's continue. I feel like the second example, what do you guys think? 25 is a perfect square number. 16x second power is also perfect square number, but it looks like maybe matching with the second one, but there is no radical. There is a little bit of typo, so there's no radical. If you go up, 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 there's no radical, right? Except for the second one. So therefore, this is not exactly u second power, means x second. You have to get rid of 16. So what I'm gonna do, we're gonna factor out 16 to match with number 2, right? So if I factor out, what happened? Integral 16 factor out So 25 over 16, because when you multiply, it goes back to 25. And then I factor 16, x to second power remaining, dx. Good. And then I can bring 1 over 16 to the front. Integral 1 over 25 over 16 plus x a second. Exactly. This is my perfect square number. And it is matching with number 2 right now. A second plus u second. So this is a 5 over 4 times a 5 over 4. So a will be 5 over 4. And then this is a u second power, so u will be x. So we have what the u and a. And then this one will be 1 over a tangent inverse u over a plus c. So if I'm plugging in, so let me copy this. So we have all the information now. So get rid of this part. So therefore we have a is what? 5 over 4 tangent inverse u is what? X over 5 over 4. So I'm going to simplify a little bit. Then I'm going to minimize a little bit this one. So it is going to be, I'm going to bring this one up. So it is going to be 4 over 5 tangent inverse 4 over 5x plus c will be the answer. Does it make sense to you? And then I forgot something here. If you remember, we have a 1 over 16. So here I still have 1 over 16 right there. 1 over 16. So if I keep multiplying 1 over 16 right there, right, we flipped over, they're going to cancel. So 4 times 4, 16. So 4 times 5, it's a remaining. So 1 over 20 tangent inverse 4 over 5x plus c will be the final answer. So let me just minimize it a little bit. So plus c. So that's your final answer. Are you guys okay with that? So just to look at the step-by-step work, I'm not using any fancy techniques here. I'm literally following the step that we are given. So we have a 1 over 25 plus a 16x to the second. So that to match with the second techniques, I have to get rid of 16 because the 16 is not part of the u. So to have solely x second power, I have to factor out 16. So when I did that, 16 is outside of the parenthesis, 25 over 16 inside of the parenthesis plus the x second power. Because if you do the backward distributive property, you're going to go back to exactly 25 plus the 16x to the second power. So from there, 1 over 16, came to the front. And then take the integral. So now 1 over 25 over 16 plus x to the second power. That's exactly what I'm looking for to match with the second number second identity. So we define from there, a is a 5 over 4, u is x, and that should be resulting in the inverse trigonometric function 1 over a tangent inverse u over a plus c. So we know all the a and u. Bring it back. 1 over 5 over 4 tangent inverse x over 5 over 4. But don't forget this 1 over 16. So we have to keep multiplying it. So when I did that, you will get the final answer right there. Okay, so think about it. When when the denominator of the function include a perfect square number, the outcome, the integral results in what? Inverse trigonometric function. So that's why this 3 technique will be really, really helpful. Okay. So now we just got the concept. I'm going to practice 3 more examples, but in this time, again, what if we have, let's go down slowly. What if we have a specific interval? We are not afraid of it. And then I'm just keep giving you the 3 technique. I don't know why there is a radical, so let me get rid of it. The second one, there's no radical. Yeah, we good. So let's take a look at the next question. So we know this is beautiful. Inside of the radical, 1 is a perfect square number. X second is a perfect square number, exactly matching with number 1, isn't it? So we know 1 is a 1 times a 1. X squared is x times x. So from here, A is 1, U is x. You can catch this. So the outcome will be, include the sine inverse U over A plus C. So now I know what the U, sine inverse X over 1 plus C. But here we have from 0 to 1. That's the interval, correct? So instead of writing C, let me just finish up from 0 to 1. That means capital 1 plus minus capital 0. So you're going to subtract large minus 0. That's integral with the definite integral. So this is a sine inverse from 0 to 1. I forgot the x. So sine inverse x is 0 to 1. So if you're plugging in 1 minus sine inverse 0, sine inverse 1, you will get pi over 2. If you don't know what that is, go to decimal. They can calculate it as well. This is going to be 0. So the answer, pi over 2. So this is the definite integral resulting in inverse trigonometric function. It's the same strategy, but then we have a specific interval so that you're going to subtract from large and minus. Yes, we got this. So let me bring this one a little bit smaller. Okay, let's take a look at the second question. So 1 plus x second power, what do you guys think? This is exactly matching with the second, a square, number square plus variable square. So this one, I can see a is 1, u is x. So this one resulting in inverse trigonometric function with the tangent. So 1 over a, tangent inverse, u over a plus the c. So we know what the a, 1 over 1, tangent inverse, 1 over u as x. U is x over 1. And then we have from 1 to radical 3. We have a definite integral. So that means tangent inverse x, because 1 over 1 is just 1, from 1 to radical 3. So that means, we know it means, let me minimize a little bit. So this means capital radical 3 minus capital 1. So if you're plugging in tangent inverse radical 3 minus tangent 1. So you're going to subtract by using the decimal. Go to decimal, type that answer. You will get 0.261, very small portion. So that's what we are utilizing the, perfect square information to find out where the integrals resulting in inverse trigonometric function. Okay, so how you feel? Getting better and better. So you're literally matching one of them. Okay, so just 2 more definite integral. Let's keep practicing it. So I see the perfect square number. And then I see this is exactly matching. What do you guys think? This is matching with the third one. Why? Because this is corresponding u. This is u squared minus a squared. 1 times 1 is 1. So we have all the information. What? U is x, a is 1. So this is going to result in 1 over a secant inverse u over a plus c. So let's plugging in 1 over 1, secant inverse x over 1. And here we have from 1 to 2 radical 3. So if you simplify secant inverse x from 1 to 2 radical 3, and then we know what that means. It means capital 2 radical 3 minus capital of 1. So plugging in secant inverse 2 radical 3 minus secant inverse 1.
Again, go back to decimal, enter secant inverse to radical 3 minus the secant inverse 1, you will get simple decimal 1.278. So check it out with the decimal as well. Okay, getting better and better. One last question. So here, right, I do see the perfect square number 4, 2 times 2, x times x. So this is exactly matching with the second one. So a is a 2 because 2 times 2. U is going to be x. So what I'm saying is this is matching a squared plus a u squared. So a is a 2, u is x. This result in 1 over a tangent inverse what? U over a plus c. And don't forget the definite. So we already know a 1 over 2 tangent inverse x over 2 and then from 0 to 2. That means capital letter of 2 minus 0. So you're going to plugging in 1 over 2 tangent inverse when 2 minus. So this one is a capital of 2. The next one, 1 over 2 tangent inverse. 0 over 2 is a 0, isn't it? So you're going to simplify this information. So it means 1 over 2 tangent inverse 1. 1 over 2 tangent inverse 0. Again, go back to decimal, enter those expression. You should get 0.392. So that's the outcomes. When the function is getting involved with the perfect square number, then you see that the outcome result, the outcome also get involved with the one of the inverse trigonometric function. So that's all about it. 1.7 is a very, very short topic and short techniques. Sometimes you might be hesitating. You might be hesitate that, oh, should I have to use a composition function? Yes, you could try that. But again, it's going to be more complicated. Let's say, hey, this is u equal to x second minus 1. You're going to take the derivative, so du equal to whatever. But still, you need to find out what the 1 over x times dx is going to be in terms of the u variable. So it's more complicated. It takes a long time. You have to change the integral in terms of x2, in terms of u variable. It takes a long time, isn't it? So just look at the pattern. Look at the pattern in this question. The key point is perfect square number. And then if you see one of this format, the outcome is going to be getting involved with the inverse trigonometric function. So that as you see that, this is a much simpler and shortcut, and you can deal with many different type of function, with the variety of options. Okay, so that's 1.7. It's really relevant to all the topic we talked about. So we finished chapter 1. How you feel? Okay, so I just want to mention one more thing. While you are taking the quizzes, there are 3 attempts, right? Each quiz has 3 attempts, and then there are many embedded video that I also posted it. So you can watch the video on quizzes. There are many available videos nowadays. You can, watch each embedded video explaining, how to solve each number of questions. So that'd be really helpful. And then definitely my lecture note and videos are all the time available. So check it out. So there are, checkpoint chapter 1 quiz at the end of the chapter 1. So this includes entire chapter 1, concept. So in this time, you have only 2 attempts. And then the final answer will appear after the second attempt. But whatever the quiz is, you have 3 attempts. You can keep practicing it as much as you can. So now you can finish entire chapter 1. And then if you have any question, feel free to join our chapter 1 discussion and helping each other. And I will reply to your comments. If you have any question, email me as well, okay? So hang in there. You guys have been doing awesome. Yay, we congratulate for a second. We finished chapter 1. So in the next video, we're gonna move on to the new chapter,
3. We're going to begin with chapter 3 first. Okay. So thank you everyone for watching this video. I will see you in the next time. Bye-bye.